Hello everyone. Today I'm going to demonstrate and show to you guys the system that I have built around the PIC24 FV16 KM202 microcontroller. In this project I'm designing a digital oscilloscope and spectrum analyzer. And PIC24 is acting as the ADC module. So it used one of its 8-bit ADC pin to digitize an input signal. In this case, the input signal is generated using a wave generator. And so at the request at the request for data by the uh, C# GUI application here, PIC24 will gather portion of its sample data and send it to this GUI application for display so that the user can visually analyze the data. And it does that by communicating with a Bluetooth module here, the RN42. It's communicating with the Bluetooth module using the UART protocol at a baud rate of 115 kilobits per second. So this C# GUI application is developed using Visual Studio Windows Form application. And in order to demonstrate, let's first connect to the Bluetooth module. Communication has been established successfully. Let's start. Here, the different features that this GUI application have is that it have 3 buttons for user to control, to start, stop, and clear the Z-graph plots here. So we have 2 main plots here. I will go and explain that later on. So here at the bottom we have multiple text box and 1 combo box. The combo box allows the user to select the different sampling frequencies. It's important to note that the maximum sampling frequency that PIC24 can perform is 270 kilohertz. Let's use that. So we see that higher sampling frequency, we get better resolution of the sampled signal in terms of the time domain. So we are generating our wave generator is generating a 4 kilohertz sine wave signal. And so here is a 10 kilohertz sampling frequency, 50 kilohertz. So the higher we go, the better the resolution is. So here is maximum sampling frequency, 270 kilohertz. And the other text box allows the user to look at the maximum, minimum, and peak-to-peak voltages of the sampled waveform, and as well as frequency content. And here shows the last one is the FPS of frame per second, so the refresh rate of these 2 plots. And so to the left we have the time domain waveform, and to the right we have the frequency, the spectrum analyzer, so the frequency spectrum of the waveform that we're digitizing. And this GUI application is implementing the DFT to determine the frequency spectrum and the frequency that the signal have. So in this case, it's 4.2 kilohertz. So it's not accurate due to frequency resolution of the DFT, which is fs over n. So in this case, 270 kilohertz over 256, since I'm sampling 256 data and a packet and send it over for the DFT to perform. So different features and for the time domain include track bars, so triggering track bars, the zoom to left and right, shifting, zoom in and out, shifting left and right, and here in the center here, two track bar to enlarge waveform in the case of small signal, so we can enlarge it. And here the magic box act as the auto, just like the auto button on a oscilloscope or the commercial oscilloscope here. So we know that auto button will auto scale and auto trigger the input signal, and this here does the same thing. So let me decrease the amplitude of this signal. So I'm decreasing the amplitude, and let's say that I am playing with the trigger. So I'm playing with it, and we see that, let's say we go out. When we go out of trigger mode, the triggering, we have a unsteady signal. But if I were to bring it back in to the right range, we will see a steady signal. So now we're out of range, and the signal is not steady in terms of displaying. But with the help of this magic box, I can click auto trigger, and there we go. It auto trigger, and I can also click auto scale, and it will automatically enlarge the signal to fill this plot, so we can better analyze this signal. I can further say increase the frequency here and see the effect of it. So the refresh rate is not as bad, increasing here and decreasing, and we can see the change right away. Let's go back to 4 kilohertz. Let's look at the frequency spectrum analyzer. As I increase, we can see that it's also increasing. Do this. Here it's increasing. So here is 4 kilohertz, 40 kilohertz right now. Our system determines it to be that's about right. That's good enough. 40 kilohertz. So here is the time domain content of the sampled signal. It's not as good, but it does serve the purpose of this project. So let's decrease it down to say 5 kilohertz now. So I can zoom in. I can also shift left, shift right. And while I'm doing this, the waveform is coming in live. So nothing is being stopped it. Now let's increase the amplitude now. Let's increase the amplitude to 5 volt, peak to peak. Okay. So we see that the waveform goes beyond the scope of our plots. So we can manually use this to control it. Otherwise, we can click the auto scale button here, and it will auto scale it for us. Also, just click auto trigger. There we go. And so let's use a wave that's a triangular wave. There we go, triangular wave. Let's decrease the frequency down to something that's super small, say 500 hertz, and let's decrease the sampling frequency to 50 kilohertz, 10 kilohertz. And here is the frequency content of the triangular wave. So we see that I have a lot of harmonics here. unlike the sine wave where it only have one harmonic, one fundamental harmonic. Let's go back to the sine wave. There we go. That's the sine wave. And so this is the demonstration of my system. Thank you for watching.